It's a great pleasure to introduce our own Volodya Retakh, who will talk about non-commutative generalized Catalan numbers and the generating functions. As usual, you're welcome to interrupt any time if you have anything to say, but otherwise, please mute yourself. Thank you.
Okay. So thank you for the invitation. So this is, I'm talking about part of a joint work with Arkady Berenstein from Oregon and Michael Gekhtman from Notre Dame. And this is a part of a project which is non-commutative theory of everything. So I will try then to concentrate now on this Catalan. So Aigner in 1999 introduced what he called generalized Catalan numbers. And this is just, so you have just this three diagonal matrix in his paper with the ones on the upper and lower diagonal, and then numbers on this on the main diagonal. And he took actually the powers of this matrix A and the northwest element of the result, and he suggested to call it generalized Catalan. And now it was justified by several examples. For example, if S naught is 1 and other elements on the diagonals are 2's, then you are getting Catalan numbers, classical Catalan numbers. If you have only ones, all ones on the main diagonal, then you have Motzkin numbers. And then if you have just zeros, then those central binomial coefficients. Okay, and also Aigner showed that if you take these generalized Catalan numbers and you consider Hankel matrix, which you can see, then the determinant of this matrix is 1. And yes, that's true. We know that this is true for Catalan numbers and for Motzkin numbers. And he also computed determinants for such matrices, but which starts with not with the C naught, but with the C1. So there's a formula, and again, you know that for classical Catalan numbers, the formula is also gives you 1. Okay. So then you see this, you have actually two temptations. One is to consider just other classes of matrices, and another one, in our case, consider matrices over non-commutative rings and see what happens. Well, the first example is that you consider matrices of ones and zeros. So you have exactly k ones in the upper row, then k plus 1 ones in the next row, then k plus 2 in the next row, and so on. And in this case, the generalized Catalan numbers. So you see this formula, they're just kth fifth Catalan numbers. Okay, so that's one example. And another example is the following, that now you consider just metrics when you have just ones on the upper diagonal. And then here you have the same diagonal, but shifted, shifted, for example, in the left column. You see this, there will be k zeros, then 1, then zeros, and then like you're going up to diagonals. And so in this case, this is actually So if n is not divisible by k, then you have zeros. And if n is divisible by k, km, so then they are first Catalan numbers. So m, for m equals 0, 1, 2, and so on and so on. Okay. Now, but probably, I don't know, Neil probably knows all this. Okay, now the general approach is actually, first of all, we are trying to write generating functions. And it turns out that the technique of quasi-determinants, which for working with matrices of non-commutative rings, is quite useful in this case. So let me just maybe remind the definition. Quasi-determinants. Okay, so suppose A is just a square matrix over an associative ring. So I will introduce notations. Aij, upper Ij is the submatrix obtained when you remove the row number I and columns number j. And then you also have this row number I. So the whole row without Aij, and similarly for the column. And then you have just this strange just sort of rational function, because you require that this submatrix Aij is invertible. Okay, okay. Just I will give you just an example, and say for n equals 2, which is written. So here the answer, for example, if you want to get this quasi-determinant with the index 1, 1, then you have A1, 1. Then you have this row without A1, 1, you have it's A1, 2. Then you cross the first row and the first column. The remaining matrix consists of A2, 2, so you have A2, 2 inverse. And then the column will give you A2, 1. And so in here you have also other examples. Okay. All right, and okay, and now this is actually a special case of Schur complement, and it looks actually not so nice, especially for when you consider n by n matrices. And so, but the only there are actually two justifications. First of all, what is convenient. These expressions, they have sort of categorical meaning. You see that, so you may compose A12 and A22 inverse, so you may think about morphisms or letters attached to directed graphs, to edges of directed graphs. So this is rather rigid. So the formulas are rather rigid, and this is very useful because it basically gives you a hint what you can multiply and what you cannot. Plus, there is a technique how to work with this, with such expressions. So that's, I will not use the technique, I will show only corollaries from this. Now, how this definition actually fits into the known expression. So actually, they're related to the elements of the inverse matrix. That's they defined even when it is not invertible. And again, in the commutative case, this is just relation to this. So determine just the ratio of these two determinants up to a side. And now, for sometimes, as for notations, it's actually convenient to box the. So this is the Aij for this quasi-determinant. This is just an example. Now, okay, let me now convince you that this definition is useful. And here is the first application. So now I will consider just three diagonal matrix, but with just general entries. And I will define then generalized Catalan numbers, as I did before. And then I will consider Hankel matrix and its quasi-determinant. And the answer is, you can see that this is basically, again, if those are morphisms, so then you have just composable morphisms. So you go from A0, 1 to AN-1N, and then you go backwards. Well, again, if in the Aigner's case, if the elements of the upper and lower diagonal are 1, so the result is 1. And if you want to get so the determinant, you consider this quasi-determinant, then you cross out last row and last column, consider next quasi-determinant, repeat this procedure, and you will multiply the results. So you have 1. So the Aigner's result follows from this one, which is more general. And again, as I see that such expression is composable, just expression. And now you have actually the symmetric expression for Hankel matrices, which starts with a C1. And so in this case, you have basically the same expressions that you see before, except that in the middle you see this quasi-determinant of this initial, actually of the initial n by n submatrix. Okay, and so from this also you can get formulas that were stated by Aigner. All right, now then there's actually a second determinant, second application, and this is for semi-infinite matrix Aij. Now I consider submatrices which starts with their Aij, with this inequality for numbers, and just to write this in a good way, I have to introduce this inverses. And for if A is a low Hessenberg matrix, which means that you have just a low triangular matrix plus 1 upper diagonal, then you have the following result. Well, of course, if this infinite sums if you can justify this infinite sums, so you need to put something to 0 and so on. But again, if you see, again, this so those products, again, they have actually categorical meaning, because you multiply B0 by A01, then by B1, and so on, and finally you arrive to AK. Okay, and now I will apply this theorem actually to just a special case. So again, this is Hessenberg matrix. I will define actually then generating functions for these non-commutative Catalan numbers, which actually starts with pk. So here is just the the definition.
Volodya,
Yes.
in particular, if you plug in matrices, you get the identity matrix. If you plug in everything 2 by 2 matrices, can you make it more concrete by, it's all non-commutative, right? All these variables.
Yes.
So if you specialize to 2 by 2 matrices, you can make sense out of it and get something?
Yes, absolutely. No, I can actually make sense of this if I have the finite number of elements in the left column. That's an example, but also I can do this in general because I will introduce this central variable t.
Thank you.
And then I will make sense of this. Okay, and this is actually what I will do. So I can define actually then generating functions for Catalan numbers, but this is basically, I do this by taking, if I want to have this generating function for P, I will consider identity matrix minus P times T, and T is central. And then I will get the following formula, which is written here. Well, again, it's actually has this categorical meaning. And in this case, it has a sense because of T, those basically you multiply formal series in T. Okay, now, so what happens with the, now I would consider special cases of this corollary. First of all, assume that the element of P that I'm getting this next elements in each diagonal by implying this just some homomorphism theta. And then I have just this equation for this equation for generating functions, which, as you see, it basically reminds us just an equation for generating functions for full Catalan numbers, except that you have those shifts. So again, if you have this constant diagonal, if you have matrix with constant diagonal, you have the following equation. And now, if you consider separately just such equation, then you can just construct Hessenberg matrix with constant diagonals. So this is P01 goes under upper diagonal, and others you just take any element on the left and you go by this diagonal. So you construct this matrix. Then you take powers of this matrix. Consider this the northwest elements. And then you produce a series like this. So basically, you know how to solve such equations. Well, for example, if you have just 3 diagonal matrix, then you have just, here is your equation. And again, if you put those elements, these three elements equals to 1, then what you have here is basically characteristic equation for the generating function for Motzkin numbers. So you may consider this example. So this is as a, you can define non-commutative Motzkin numbers depending on 3 parameters by using this equation. Okay, and the other example is like this. So now suppose I have this 2 diagonal Hessenberg matrix with the ones on the upper diagonal, and here I have elements of Z1, Z2, and so on, which obtained by this shift. Then I have again these equations on generating functions. And now again, if I consider this generalized Catalans, they will be equal to 0 unless n is not divisible by k. And if it is divisible by k, I have just this equation for generating function. So what? And finally, I can write it like this. And if I specialize again those z's equals to 1, I have just this is first Catalan numbers with the index k. Now let me consider another model for Catalan numbers. So assume that I have 3 variables, x naught. Yes.
Are the x sub i's commutative now, or still
No. They are 3 variables.
So non-commutative 3 variables?
Yes, non-commutative 3 variables.
Okay, thank you.
No 0, so infinitely many. Okay, and then I can consider actually this. So I can consider this the shift homomorphism, which xi goes to xi plus 1. And then I can just continue the theta to say to Laurent polynomials. And now I will consider this matrix, as you see. So which you see here. And now each diagonal, actually these elements on the each diagonal are obtained by shifts. So for the first diagonal, I have x1, x0 inverse, then x2, x1 inverse, x3, x2 inverse, and so on. Now, and next diagonal starts with x2, x0 inverse, and so on. So I have this P. Now from this matrix P, I want to obtain other metrics. So what I will do is the following. I will take this matrix A, so this is just one sort of upper diagonal, and I will multiply if I multiply E by P, I get the submatrix of P just with the upper row removed. If I will multiply by E squared, it means that I'm removing 2 rows and so on. And if I remove S rows, I call the corresponding Catalan number just well, this is non-commutative Catalan number, and actually the index is s+2. So in particular, when s equals 0, I'm getting what's called non-commutative Catalan numbers. They were introduced by Arkady and me earlier, but using another model. Okay, then let me introduce just this generating function.
Volodya, so these non-commutative first Catalan numbers are really non-commutative polynomials in
They are Laurent polynomials.
So in particular, the number of terms is a first Catalan number?
Yes, exactly, yes. Yes.
So,
and so this is why we call them actually non-commutative Catalan numbers. Of course, this is sort of abusing of just language because they are not numbers.
Right.
They are Laurent polynomials.
Right, but is the number of terms, if you expand it, is that number, right? So
yes, exactly. If you will specialize everything to one, then you get first Catalan numbers.
So since the first Catalan numbers, and more specifically the Catalan numbers, count certain combinatorial object, for example,
yes,
paths, you can associate.
Yes. We will come to this. I will talk about paths.
Great.
So we will come to this. But so here you have so if you introduce these ratios, then you have these equations for this generating functions, which again actually reminds you of equations for generating functions for first Catalan, for standard first Catalan. All right, now I will try to give you a combinatorial interpretation. Okay, so first of all, so I will, for me, first Catalan number is the number of passes on the grid, and from the 0, 0 to the point n, and then k-1 times n, and which consists of move. You're moving to the right and up, and you must be below this line y equals k-1 x. So in particular, if k equals 2, you have just this standard Catalan numbers. Okay, now then, depending how you call it, you can call Dick paths. Also, there are another versions of Dick paths, or you can call Catalan paths. Well, again, Doran, you are an expert. You have to tell me if this is the right terminology.
Yeah, basically, except Dick paths, you draw it a little bit different, horizontally.
Yes. Okay, so just this one. Now, I'm interested in corners on this path. And to each corner of this path, if P is a corner, then I have this integer, which I call actually content. So C of P, and here the formula. You have k-1 times P1 times the first coordinate minus the second coordinate. And since all my paths are below this straight line, y equals k-1 x, C of P are always non-negative. Again, for k equals 2. This is just the easiest way. This is p1 minus p2. Okay, now you have these corners. There are two types. One is southeast corner, so you go right and up. So just right and then up. And another opposite, northwest, when first you go up and then to the right. Then to each of these corner, so that it has sort of a signature or whatever you call it, W of P, and W of P is 1 for southwest corners and minus 1 for northwest corners. Okay, and so to each path, I'm assigning just a product. Actually, this is a Laurent product. So X with a number C of P, which is an integer, which is non-negative integer, and with the power 1 or negative 1. So I have to say that in many cases, when you are dealing with the free variables and you are trying to write Laurent polynomials in different situations, you always have this alternating powers 1, negative 1, 1, negative 1, 1, negative 1. So there's, okay. Now, if I have this, I can consider the sum of these monomials corresponding to all Dick paths from the beginning to end. And this is exactly the Catalan numbers defined by this matrix. Actually, we removed some rows. Okay. And now, and this is again now, but this model for k equals 2, basically it was introduced before. This is just for Catalan numbers when k equals 2, and it was a model used by Arkady and me. All right, now let's compute these determinants of Hankel matrices, because so we know again, let me remind you that in the sort of commutative case, so if you take the Hankel determinants defined by Catalan numbers, and this determinant starts with a 0, with a C0 or C1, then the answer is 1. And you can use this as a generalization, as a definition of Catalan numbers. Catalan numbers obtained by from solutions of this determinant equation. Now let's try to do this in the non-commutative way, using this. And here's the answer. So the answer, but of course I have computed quasi-determinants, and the quasi-determinants are computed. This is just equal to my free variables. So as soon as I specialize all my free variables to 1, the answer is 1, and from this it follows that the determinant equals 1. Okay, I should add that actually when we started to think about non-commutative version of non-Catalan numbers, we started with these quasi-determinants, and then we solve this equation for this non-commutative Catalans, and then we interpreted this by using these patterns. Okay, now I have a temptation to consider other non-commutative numbers, which are Narayana numbers. Okay, it has Narayana numbers. There are a lot of interpretations. So this is here are much better expert than I am. Here is just the formula. This is 1 over n multiplied by n choose k and choose k minus 1. But actually, again, that's if you want to count Dieck passes, but the passes which go from, from 0, 0 to n below the diagonal, basically, and then for each path, you basically, so you count horizontal moves. And this is also Narayana. Now, what about non-commutative stuff? And actually, I'm getting non-commutative versions if in my matrix P, I introduce this parameter T in some places. So I will not explain how, but just believe me that I have to put in the right things. And then the generalized Catalan numbers will be polynomials in T. And the coefficients will be again Narayan, standard Narayan. This is non-commutative Narayan numbers. If you specialize them, then you get classical. First. All right, now just so I will talk very briefly now about orthogonal polynomials. Okay, so first of all, one of the way to introduce orthogonal polynomial, the classical way, is to define so-called moments. So if you have just a measure, and then you integrate t to the I or this measure, you call the results C0, C1, and so on, depending on t. And then you can just define orthogonal polynomials as the ratio of this determinant to another determinant when you remove the last row and last column. Another way, you define this as quasi-determinant. So you can actually imitate this procedure in the non-commutative way. And in this case, you have to suppose that you have a ring R with the anti-involution. So the square, so if you know this double overlines will give you over A, will give you A, and you have to read all words from right to left. And so suppose you have these elements and which are stable under this involution. Okay, then this you can define these orthogonal polynomials. And so they were defined in this long paper on non-commutative symmetric functions with a long list of authors. So there were like 6 authors. And Gelfand called it the hexagon paper, but this one. But in any way, so you have just this definition. And this element Ci's, They are just abstract, non-commutative moments. Okay, but you need to have some orthogonality condition. And the orthogonality condition is given like this. If you need just to consider this bracket between a times t to the I, b times t to the j, you have this product a times c, I plus j, and b just, and then b overline b. Okay, and then this is really non-commutative. And so, and then this is really orthogonal polynomials in this case. And okay, then you have to satisfy, then you have to standard orthogonal polynomials. They have a recurrence relation, which actually connect polynomials with the number n plus 1, n, and n minus 1. And if you use these non-commutative Catalan numbers, then you have just, well, rather simple, actually, relation, which you can see just over there. So this is so this is just, so you can specialize this in the commutative case if you wish, and so on. But you can also compute those polynomials. And I'm actually a little bit, okay, and the answer is the following, that the coefficients of these polynomials are so-called non-commutative binomial coefficients. Again, they were introduced by Arkady and me when we studied actually non-commutative Catalan numbers. And okay, and so I will not give you a definition. So just if you are interested, I can give you a reference to the paper. Okay, and so then maybe I will stop here. Just so let me repeat that actually, if you are interested, and then you may consider actually a lot of other matrices and start actually this commutative or non-commutative generalized Catalan numbers defined by these matrices. Okay, and so on then here, okay, maybe I'll stop. So this is.
Thank you, John.
Okay.
We have some minutes for questions. I have a quick question.
Yes.
So is a general theory of non-commutative orthogonal polynomials analogous to the classical theory of?
Yes. Yes, but yes, it is. So I mean that you take just this model. Sorry. Okay, so okay, so you have just this definition, and then you may compute sort of just you have just this definition, and from this definition you just may get this recurrence relation. So there are formulas for the coefficients, and also then you can get what's called total lattices associated with orthogonal polynomials. So this, there is a theory and so on, but there were there were like parallel groups, because so we did this actually in the pure non-commutative case, but there were actually, you know, in Berkeley, so there were like several people who worked just with moments as matrices.
Yeah, so you have moments, non-commutative moments also. That means,
Yes, yes, but if you do with matrices, of course, you can you use more analysis here.
yeah. Another quick question. So Catalan numbers is a two-dimensional works. Is there any way to extend your beautiful theory to higher dimensions? So the analogs of
So we didn't think about this probably, but I don't know. So if you just point me to some interesting commutative case, which is just related to multi-dimensional grid, it would be nice.
Okay, thank you.
Okay, then then of course maybe you can use the theory of hyperdeterminants, but then
yeah, probably behind.
Yes. Okay.
Other questions for Volodya? Well, thanks again, and see you next time. Thanks so much. Robert will end this. Thank you. Okay, bye bye. Thank you.
Bye.
Thank you.